Hello. For these set of notes and this short video, I'd like to describe some fun things happening following chronic aerobic exercise or aerobic training. So this is out of chapter 13 of our book that are adaptations due to aerobic training. And I would like to focus on VO2 max and the VO2 max equation, or the VO2 equation, which is sometimes called the Fick equation for oxygen consumption. And from this slide, we know that VO2, and I'll look at the middle bullet point, VO2 is equal to cardiac output times A minus V oxygen difference. A is arterial oxygen and V is venous oxygen. So that difference can be thought of as extraction. So we're extracting O2 out of the blood. Q, or cardiac output, is heart rate times stroke volume. And cardiac output is liters of blood leaving the heart per minute. And that can be thought of as delivery. So I would like to focus on how aerobic training, we know that's going to result in an increase in VO2 max. So what will increase? Will delivery increase? Will extraction increase? And if so, how will aerobic training result in an increase in delivery and extraction? So if we look at some of the cardiovascular adaptations, that left ventricle does become a larger size. So that would result in bullet point number 3, greater stroke volume. Also with training, there's a greater plasma volume in the circulation. So a bigger left ventricle size, a greater plasma volume, all are going to equal a greater stroke volume, the amount of blood coming out in that heart in one contraction. We know that max heart rate is 220 minus age, so actually max heart rate is age dependent. But at submax exercise, there'll be a reduction or a reduced submax heart rate. Because of a larger sized heart and greater stroke volume and greater plasma volume, there'll be an increase in max cardiac output, and that is delivery. And we talked earlier that probably most of us are limited by cardiac output or heart size or stroke volume, so those have gone up with training. What about extraction? There's probably an increase in max oxygen extraction as well, getting O2 out of the blood. So what is extraction? Extraction can be thought of as this AVO2 difference, and how can that increase following aerobic training? Well, one is there's a faster blood flow going to the working muscles, and that's really cardiac output. But if we can get that O2 oxygen to the working muscles faster, we have a better opportunity to pull it out of that blood. There's also an increase in capillary density surrounding the muscle cell. So surrounding a muscle cell, there's now greater amount of capillaries. Also inside the muscle cell, there's a greater amount, probably a twofold increase, in the amount or the volume or density of mitochondria inside that muscle cell. So there's a greater place for that oxygen to go because oxygen acts as that final electron acceptor at the end of the electron transport chain. With my third bullet point, the increase in capillary density, the blood flow actually slows down in the muscle bed itself. So as the blood flow in a capillary passes by a muscle cell, that flow will actually slow down. And I always think of like a boat example. If you're whitewater rafting, that blood flow is really, really fast, or that water is really, really fast. It's hard to paddle over to the shore. If the river widens out, now the same volume of water is going through this nice wide river. and it's easier to paddle over to the shore and drop someone off. With greater capillary density, the blood flow will actually slow down as it passes the muscle cell, and that's easier then to allow oxygen to be dropped off, and also other things we've talked about. Easier for lactate to be dropped off, easier for glucose or a fatty acid like palmitate to be dropped off, easier to pick up carbon dioxide. So blood flow will actually slow down in the muscle bed itself.